In 1907, the North Atlantic passenger trade was locked in a fierce corporate rivalry. The undisputed champions of this route were the ships of the Cunard line, specifically the Lusitania and Mauretania. By maintaining the highest crossing speeds, these vessels firmly held the prestigious Blue Riband. To counter this, White Star Line executives, including Managing Director J. Bruce Ismay and Harland and Wolff Chairman Lord Peary, realized they could not win a pure speed race. They executed a strategic pivot. They would concede the speed records entirely, focusing their resources on building vessels of immense scale and luxury. The economic engine driving this strategy was the immigrant market. With nearly 900,000 travelers entering the United States each year, White Star moved its express service from Liverpool to Southampton. This geographical shift allowed them to directly capture the massive wave of continental European traffic. The ship born from this strategy, the Titanic, was designed as a calculated economic tool to monopolize transatlantic travel. The goal was to offer a passenger experience so massive and comfortable that crossing time became entirely irrelevant. The physical manifestation of this ambition took shape in the Harland and Wolff shipyards in Belfast. The finished vessel measured 882.5 feet in length, spanned 92.5 feet across, and had a gross registered tonnage of over 46,000 tons. This diagram shows the Titanic's enormous footprint compared to standard vessels of the era. To move a structure this large, the ship relied on 29 boilers feeding a triple-screw propulsion system. This plant outputted 46,000 horsepower, allowing the heavy ship to maintain a steady cruising speed of 22 knots. Inside, the first-class spaces were built to project absolute security and comfort. Passengers had access to Turkish baths, a fully equipped gymnasium on the boat deck, and a dining saloon capable of seating 550 people simultaneously. Looking at this lateral cross-section of the hull, we see the architectural feature that earned the ship its famous Unsinkable moniker. The base of the ship was divided into 16 separate watertight compartments. The massive scale of the engineering created an illusion of total safety. Beneath the luxury, the design contained structural compromises that would soon be tested. On the night of April 14, 1912, the ship was cutting through the Atlantic at 21.5 knots. The outside temperature had dropped below freezing. At 11:40 p.m., lookouts spotted an iceberg directly in the vessel's path. First Officer William Murdoch immediately ordered the helm turned hard a starboard. This animated diagram contrasts the physics of that maneuver. A head-on collision would have engaged the ship's reinforced bow, utilizing it as a crumple zone. By turning, the ship sideswiped the ice, exposing a much larger section of the starboard hull to direct contact. A 1991 metallurgical analysis by the CanMet laboratory on pieces of the recovered hull revealed a critical material flaw. The steel plates, manufactured in Scotland, contained a high sulfur content by modern standards. When subjected to 29° Fahrenheit water, this specific type of steel becomes highly susceptible to brittle fracture. Instead of denting or slicing cleanly, the steel shattered on impact, popping 3 million rivets and cracking open the seams along the contact zone. The shipbuilding materials of the era were unequipped to handle the immense stress of a glancing, high-speed impact in sub-freezing temperatures. The collision opened several small, varying-sized holes along the side of the ship, ensuring a fatal intake of water. Returning to the ship's profile cross-section, we can identify a severe architectural flaw. The transverse walls dividing the 16 watertight compartments only extended a few feet above the waterline, stopping at E-deck. Critically, they were open at the top. This was a deliberate choice. Capping the bulkheads or extending them higher into the ship would have disrupted the layout of the upper decks, reducing the square footage available for the expansive public rooms and luxury suites. As the breached forward compartments flooded, roughly 16,000 tons of seawater weighed down the front of the vessel, causing the entire ship to pitch downward. Because the ship lacked a double hull on its sides to contain the initial breach, the forward pitch forced the accumulating water to spill over the top of the dividing walls. As one compartment filled, the water crested the open bulkhead and flooded the next in a domino effect, pulling the bow deeper. By prioritizing wide-open interior architecture over full vertical bulkheads, the ship's designers created a continuous chain reaction. The White Star Line's pursuit of commercial luxury mathematically guaranteed the ship's sinking. The structural failure immediately exposed a severe logistical failure on the deck. The ship carried 2,223 passengers and crew, but was equipped with only 20 lifeboats, providing emergency seating for exactly 1,178 individuals. This capacity strictly adhered to British Board of Trade regulations, which only required lifeboat seating for 962 people. The regulations were severely outdated and ignored the massive scale of the new ocean liners. The rescue operation fell to a nearby Cunard vessel, the Carpathia, under the command of Captain Arthur H. Rostron. Pushing its engines to a dangerous 17 knots, the Carpathia dodged icebergs across 58 miles of ocean in the dark, arriving at the distress coordinates 4 hours later. They successfully took on 705 survivors. More than 1,500 people were lost to the freezing water. The shipping line meticulously scaled its engineering for commercial dominance, yet they entirely neglected to scale their emergency logistics to match the size of their own creation. In the weeks following the disaster, the British Board of Trade and the United States Senate launched exhaustive inquiries. The official report, led by Lord Mersey, concluded that the primary operational fault was excessive speed in a known area of ice. During the Senate hearings, surviving lookout Frederick Fleet testified that the crew's binoculars had been taken away before departing Southampton. He stated plainly on the record that having glasses would have allowed him to spot the ice in time for the ship to clear the danger. J. Bruce Ismay himself was compelled to testify, confirming that the ship's reciprocating engines were pushing 75 revolutions per minute at the time of the collision, about 21 knots. The vessel was barreling through an ice field at near top speed. For decades, it was assumed the ship sank completely intact. In 1985, Dr. Robert Ballard discovered the wreckage on the ocean floor, proving the original accounts of the survivors. The immense weight of the water in the forward compartments lifted the stern high into the air, fracturing the whole girder under the immense strain and violently splitting the massive vessel in two before it sank into the dark. Today, the severed sections of the ship sit 2.5 miles down in the Atlantic. The debris field serves as the final physical documentation of multiple overlapping failures. The wreckage illustrates exactly what happens when corporate ambition scales past the boundaries of safety engineering. Built to monopolize an ocean, it ultimately shattered against the realities of physics and the environment.